In today's video session, we are going to discuss the solution of differential equation using Laplace transform. After watching the video, the students will be able to discuss some properties of Laplace transform, explain some properties of inverse Laplace transform, and try to solve the differential equation using Laplace transform. Outline of the today's session is properties of the Laplace transform, solution of differential equation using Laplace transform, and some problems for assignment purpose. Before going to discuss the solution of differential equation with the help of the Laplace transform, let's recall some important properties of Laplace transform. To solve the differential equation with the help of the Laplace transforms, we need the major property, that is the Laplace transform of the derivative. So, the Laplace transform of the first order derivative, that is y prime of t, is nothing but sy of s minus y of 0, where this y of s is nothing but the Laplace transform of y of t. On the same line, the second order derivative, that is the Laplace of y double prime of t, is nothing but s square y of s minus sy of 0 minus y dash of 0. Similarly, we can find out the third and the fourth order differential. On the same, the first shifting theorem for the Laplace transform, that is Laplace transform of e to the power of at into f of t, is nothing but the Laplace transform of f of t, that is f of s replacing s as s minus 1. Again, one more property, that is the multiplication by powers of t. The Laplace transform of t to the power of n into f of t is nothing but minus 1 to the power of n and nth order derivative of f of s with respect to x. Now, let's consider the initial value problem, that is y double dash plus y is equal to t with initial condition y of 0 equal to 1 and y dash of 0 equal to minus 2. Now, our aim is to solve this differential equation with the help of the Laplace transform. That means we have to find out the relation between y and t, that is the independent variable t, such that that relation should satisfy this differential equation with the initial condition. So there involves major three steps. First, apply the Laplace transform on differential equation, use the properties of the Laplace transform, and then you will get the value of y of s. And again applying the Laplace inverse on y of s, we will get the y of t in terms of t, and which is nothing but the solution of the differential equation. Let's go step by step. First, we have to apply the Laplace transform on the differential equation. Our differential equation is y double prime plus y is equal to t. So, applying the Laplace transform on this differential equation. So, again for this one, we have the properties of the Laplace transform. So, here second order derivatives there. So, that's why we use the property of derivative second order, that is s square y of s minus sy of 0 minus y dash of 0. And on the same line, we have the standard function, that Laplace transform of t, and which is nothing but 1 upon s square. Now, so putting all these values in this equation, we reduce s to s square y of s minus sy of 0 minus y dash of 0 plus y of s is equal to 1 upon s square. Now, just we have the initial conditions, y of 0 equal to 1, y dash of 0 equal to minus 2. Putting all these initial conditions, we came across this equation, that is y of s is equal to 1 upon s square into s square plus 1 plus s upon s square plus 1 minus 2 upon s square plus 1. Now, here we get y of s, but our aim is to find y of t. So, by using the inverse Laplace transform, this y of s will be converted in terms of y of t. So we apply the inverse Laplace on this equation. So applying the Laplace inverse, we have that Laplace inverse of this term, and this term. Now this is the standard function. These two are the standard functions of the Laplace inverse, but this we have to solve. So to solve this one, we have to use the partial fraction method. Okay, so we have the two factors, that is s square and s square plus 1. So this is a linear and repeated, and this is quadratic and non-repeated. So the same can be written as a upon s plus b upon s square plus cs plus d upon s square plus 1. Now our aim is to find the values of a, b, c and d. Right? Now taking the LCM, we came across that 1 is equal to s cube of a plus s square of b plus d, s of a and b. On comparing both sides, that is the coefficient of s cube is 0 and here the coefficient of s cube is a plus c. So we get one system of equations or the linear equation that a plus c equal to 0, second b plus d equal to 0, a equal to 0 and b equal to 1 because it is a constant. So b equal to 1, a equal to 0, b plus d equal to 0, d equal to minus 1, a plus c equal to 0. This implies c equal to 0. So this equation reduces to this one. Now apply the Laplace inverse on both sides and using the properties of the inverse Laplace transform. Now recall the properties of the inverse Laplace transform. So it is Laplace inverse of 1 by s square is nothing but t. The Laplace inverse of 1 upon s square plus s square is nothing but sin et by a. Laplace inverse of s upon s square plus a square is nothing but cos at. Now putting all these values in the Laplace inverse of y of s, we reduces to y of t is equal to t minus sin t plus cos t minus 2 sin t, and y of t turns to as t minus 3 sin t plus cos t. So which is nothing but the solution of our initial value problem, that is y double dash of plus y is equal to t. So this is the solution of this is the procedure to solve the differential equation. So it involves the major three steps. First apply the Laplace transform on both sides, then second properties of the Laplace transform, and then we arrive to the y of s is equal to and apply the Laplace inverse on y of s, or either using the partial fraction method or some properties of the Laplace transform it. So we get the solution of the differential equation. Now these are the some assignment problems to solve the differential equation with the help of the Laplace transform.